Hello, everyone. Hey, can you all hear me at the back? Whenever I don't ask that, people can't hear me in the back, so I always check. Hey, welcome. Thank you for coming today. Thanks for being at Devoxx, and thanks for coming to this talk. There are some really, really great talks happening at the moment as well. I kind of wish I could go and see them rather than listening to me. So I'm really appreciate you deciding to come to this talk as opposed to seeing somebody else. So we're going to be talking about distributed load testing with Kubernetes. I may ask you some questions, but I can't see many of you. So we're going to start off with a quick introduction to Kubernetes, but we're going to look at it in the context of performing distributed load testing. We're also going to explore some features of the newly announced Kubernetes 1.1 and maybe look towards the future as well a little bit. And I'm Mandy Waite. I am a developer advocate. I work with the product teams, building up their products and making them suitable and useful to developers because mostly they live in a silo. They don't kind of really get what's going on with developers. So we need to come out to talk to developers, find out what they're doing, finding out what they want to do, and get their feedback and push that back into the product team so we can build better products. You can get me on +MandyWaite on Google+, or at TEKGRRL, TechGirl, on Twitter. My Twitter handle and everything is on every single slide. So if you feel the need to tweet any questions, please feel free to do so. And Kubernetes. How many of you have heard of Kubernetes or are familiar with it? Okay, quite a few of you. Probably about half and half. So we're going to go a little bit light on the details of Kubernetes here, but we're going to show it in action as well through demos. Demos that are completely new, so they may not work. You never know, which will be fun. You can laugh at me then. And Kubernetes, various different things about where the word came from and how it's said. If you are interested in learning how to say Kubernetes, then I will be outside later and I'll give you some lessons. Most people struggle with it. But it's a Greek word, and what it does really is it runs and manages containers, containers which we're all using them. How many of you are using containers today? Not as many as I thought. Wow, okay. Well, you should do. I normally have a slide saying containers are awesome, let's use lots of them. And that's where we're going with this. Containers are really, really useful. People will find much utility from them. Eventually, everything will run in a container. And at some point, we're going to want to be able to run those containers somewhere and also manage them and orchestrate them together to form applications and microservices, that kind of thing. So Kubernetes is actually inspired by something we call at Google, Borg. Borg is our internal cluster scheduler. We've not been able to talk about it until recently, but now we published a white paper on how we built it. And Borg has been going on for 12, 13 years or so, and it's been built layer upon layer, and there's things we would do differently. We could go back in time. And Kubernetes takes that learning and builds a new cluster scheduler, new container scheduler that can be used externally. We schedule about 2 billion containers per week, very lightweight containers, more like processes than anything. So that kind of number makes sense in that context. But we want everybody to be able to do the same and have the same kind of model, even if it's just from 2 or 3 nodes up to clusters of thousands of nodes. And so Kubernetes is inspired and informed by everything that we've learned over the last 12 or 13 years. Kubernetes, you'll find out more about what it does if you don't know what it does currently as we go through the talk. But today it supports multiple cloud environments and also bare metal environments as well. So you can run this on your on-premise machines, you can run it on your laptop, you can run it in the cloud. And it also supports multiple container runtimes for some value of multiple because there are not that many container formats around currently. As the container initiative, the open container initiative kicks in, hopefully we'll get to a stage where we have a standardized lower level container format. And then we may see a plethora of container runtimes, but they will all run ultimately on Kubernetes. That's the hope and the expectation. Kubernetes is 100% open source and it's written in Go, like many large-scale applications nowadays. And the whole theme to it, the ethos behind it, is to manage applications and not have to worry about managing infrastructure and machines. Although, for DevOps people, Kubernetes also is very, very useful as well, because it takes some of the nightmare out of managing configuration. So, we're going to talk about load testing, and we're also going to talk about Kubernetes. So we're going to combine the two. And this is a completely new talk. It's got some of my slides from my older decks, but it's a completely new talk. 56 minutes left. Oh my God, I can't talk for 56 minutes. Right, so this is a typical load testing setup. At least when you get outside of using AB on the command line. Now, how many of you do load testing with AB on the command line? Okay, less of you than he does, that's Michael. So yeah, so if you use AB on the command line, then this scenario may not be similar to you, although you may have scripted this. You may have scripted many, many different iterations of AB run on multiple machines. But ultimately, you're probably going to want to do this at a large scale. And the largest scale I've ever done it was for One Direction Day back in 2013, where we had to look at testing up to 20 to 30,000 QPS on App Engine. And for that, I used JMeter. So this would have been a very similar setup. We would have had master controlling everything, and we would have worker nodes that were actually generating a load and pushing them out to the system under test, the SUT, as they used to call it. So very, well, I lost the word. A very, very normal environment to see for load testing. Variations on a theme, we may have workers and also master nodes that are implemented as physical machines, physical bare metal servers, or as virtual machines, either on-premise or in the cloud, or maybe even modeled as containers. And containers, when we look at Kubernetes, start to become more like logical hosts as opposed to physical hosts that we used to have. And that's one of the key points we're going to make today when it comes to talking about Kubernetes. And this is a typical Kubernetes architecture. It used to have animations and it looks less scary, but it's not that scary, really. This is kind of similar to what we have with Borg internally. We have the idea of a master, and the master is in touch with a bunch of nodes, cluster nodes. And we'll talk about cluster nodes in much more detail shortly. And we have various services that make Kubernetes happen, things like the scheduler and the replication controller. Very, very importantly, the API server, which we're going to make use of today. And also this little thing called the kubelet that runs on each of the nodes and is responsible for really helping that node be part of the cluster. And the scheduler is one of the key things we're also going to cover in this talk as well. We also have an internal container registry as well. So you could use hub.docker.com, but we also have our own container registry for Google version of Kubernetes, which we'll talk about later. So that's on there because that's an option. But it's not necessarily going to be the Google one. It could be Docker Hub. So a quick guide to cluster nodes. So I want to kind of put this in the context of what we're going to talk about next, because you need to know some of this stuff up front. And a cluster node looks something like this. Oh, it's behind me. A cluster node has the notion of resources in terms of CPU and memory. Okay, that's extremely important. And again, it's very important to us internally. We like our engineers to be able to specify how much RAM or how much CPU, and how much CPU, a particular job that they want to run, containerized job, on our infrastructure. So we're doing the same here with Kubernetes. And so resources are effectively cores and CPU today. They may ultimately extend to other things like disk and network I/O, other things that are likely to be used up as we increase in scale. Also, nodes have optionally labels which identify something special about them. And that could be, as in this case, this machine has SSD disks. Okay, that's interesting to us because we may have something that requires the performance of an SSD disk that we want to run, in which case knowing where those machines are is important. So we can actually select nodes based on their label. It could also be something like type equals GPU, like we have a GPU in the machine, again, which is very important for specific apps. Also, we have the notion of disks, physical disks, or at least network-attached disks that look like physical disks that are attached to the machines. We could have one or more of those attached to the node. And that's important. And we're going to come back to this soon. So, what is this? Okay. So we've been struggling for a while to explain pods. And I should have given it away. So this is what a collection of whales is called. It's a pod of whales. I don't know why, because there is nothing less pod-like than a whale, as far as I can see. So why this is called a pod? Maybe there's some etymological reason that somebody can explain to me at some point. But basically, we have pods of whales. And as you can see, these whales are not the same. These whales are all different. And likewise, we have the notion of pods in Kubernetes, which is why I introduced them with that lovely picture of whales. And because often when we speak about containers, we talk about them in the context of whales. And if you know, you probably know what I'm talking about, right? Okay, Docker. I'm not wearing my Docker t-shirt. So we often talk about them in the context of Rails. So calling a collection of containers, a grouping of containers that are not the same, a pod makes a huge amount of sense, to some people anyway. And ultimately, we're not using Kubernetes to schedule containers, we're using it to schedule pods, which are effectively groups, which could be a group of one, it could be a group of two, it could be a group of others. But we're scheduling a group of containers, along with also potentially volumes as well. Volumes that are either virtual or mapped to other components somewhere else. And the pod effectively represents an application-specific logical host. So it's like taking a machine, all the things you would run on a machine, singing it up into containers, and then bundling it together in something called a pod and running it on Kubernetes. So the pods we run, the containers we run with inside a pod generally make sense to run together. It doesn't really make sense to run them individually. They live and die together. They also have the ability to talk to each other on localhost. They share the namespace, port namespace, IPC namespace. Each pod has its own IP address, which isn't natted. We can allow pods to talk to each other directly, one to each other, either on a node or across nodes. And these things are ultimately designed to be ephemeral as well. So they will come and go as we please. We can make them fairly stable, very stable in fact, but the idea is they shouldn't really maintain state, and they can be easily replaced with something that's absolutely identical. And also, we've kind of touched on this already, that pods have their own IP address. Well, they do, and that's made possible through various different mechanisms depending on where you deploy Kubernetes to. If you're using CoreOS, for example, you'd probably use Flannel, or maybe on Amazon, Flannel, and there's also Weave and Open vSwitch, which are overlay networks, which give you the ability to assign a pod an IP address, which means it has its own port namespace as well, so there's no brokering of ports. On Google Compute Engine and Container Engine, we get that naturally from our infrastructure. We get that ability with no extra cost. We don't have to do any configuration. But these are ultimately fundamental requirements of pods. We have to be able to talk to each other directly, no brokering of port numbers, and no natting. So what does our load testing look like now once we get Kubernetes involved? Something like this. So we have a master, a load test master pod, and we have a bunch of worker pods. So very much similar to what we had before, but now we've kind of abstracted it out onto Kubernetes. Slurp, slurp. Sorry about that. So let's quickly talk about groupings as well, because we need to know these things to understand what we're looking at when we get to the demo. Otherwise, the demo will make absolutely no sense, just like it doesn't to me at the moment. Hopefully it does. So labels. Labels are the single grouping mechanism within Kubernetes currently, and probably forever. You never know, things might change, but hopefully forever. And basically, we can assign labels to the objects within Kubernetes, and we have first-class objects, and we have sub-objects as well. And generally to the first-class objects, things like pods, we can assign labels. In this example, we have a couple of pods that do something, we don't know what it is, and they have a label called type equals FE. So a label is a key value pair, and it has no semantic meaning to Kubernetes. There are some system labels, but really this has no semantic meaning to Kubernetes. But it probably does to you. It probably means something to you. So when you say type equals FE, you know this is a front-end pod. And we can effectively select on those pods using the API. We can say to the API, hey, API, give me all of the labels, all of the pods with label type equals FE. And it will give them back to you. And you can build your own tooling around that, or you can build your own dashboards, that kind of thing. A dashboard's a tool, so you can build any kind of tool that consumes the API and selects on labels. And in this case, we have a pod with two labels. So pods can have multiple labels, everything can have multiple labels. And here we have another dashboard, a second one that's only interested in pods with version equals v2. So that's how labels work, and that's how we group things together. And it's a very important semantic construct within Kubernetes. And ultimately, the last thing we need to kind of understand before we get to talking about the load testing in more detail is a service, the concept of a service. So having all of these pods running is one thing, and we may have several pods that are identical or do the identical function running across our cluster. And They may be the kind of pods we want to route traffic to, and maybe want to load balance traffic across them. In that case, we can use a service. And a service does perform or can perform other functions other than just load balancing across a group of pods. But we're not going to get into that today because it just confuses things. So here we have a bunch of pods with a container, each with a single container, and each with a label type equals FE. So these are front-end pods. They're designed to serve traffic to somebody. And we create a service, and we say, service, you only care about pods with label type equals FE. And so these become the constituency of the service. And also, when we create the service, we get a stable virtual IP address, one that doesn't change. It may be ephemeral, it may be assigned from a pool, but it will be stable. And it also will be, it will have a DNS entry as well. So this is discoverable as well. So effectively what happens here, incoming traffic from a client, and the client could be some other pod running within Kubernetes, something else running within Kubernetes, or it could be exposed and routed externally. And that could be done by you with setting up routing tables and such like to point to your service, or it could be done by your cloud provider. As in the case of Google, where for Container Engine, we expose the VIP as a load balance port forwarding rule. And so traffic comes in, hits the VIP, the service will then randomly move traffic between the pods. We have session affinity in terms of client IP, but most people know how I feel about stateful pods, and having to maintain state across multiple interactions is not a really good model or a good pattern. So that's how a service works. So we've looked at labels and services and pods. We're also going to talk about replication controllers in a minute, but they're kind of like an aside. So our Kubernetes load testing service now looks something like this, where we have a service plugged in, which is exposing our master pod to the rest of the world, in this case externally, because we need to be able to access it externally, and the load test master pod talking to the workers, or the workers talking to the master. Okay. Last thing is a replication controller, and this is effectively the thing that we kind of built Kubernetes around, this idea of desired states. We create a template for creating pods, and within that, containers within the pod, and also volumes and environment variables and secrets and other things that we can put into our system. And we tell the replication to go off and manage 2 or 3 or 10 or 100 of these things that were created from the template. And it will select based on a label, in this case, role equals worker. So we're telling the replication controller, you need this template to create these worker pods. We want 2 of them at any given time. Do it. So the replication controller wakes up. It looks for pods with that label, role equals worker. If they're there, it pulls them in and they become its constituency. If they don't exist, it says, I know how to create them. I'll just send a signal to my API and say, create them for me. And the API will go off and create them for you. And at that point, we have 2 pods. And at some point, a pod may break for some reason, for some idea of breaking in how you feel you measure liveness. It could be many different ways. I don't have a slide for it today, so I didn't think it would be useful. But you can make a pod be live different ways, and you can monitor that liveness in different ways. And when the pod becomes unalive, then the replication controller's job is to create a new one to replace it. So we can maintain the fact that we always have 2. So the replication controller becomes a control loop. It's continuously monitoring to make sure we have the desired state. We have 2 of these running. If we don't have 2 of them running, it will create one or remove one. And it knows how to create them because of the template. And here's another example. This one has type equals master. Role equals master. I should have changed that type on the slides. And this one manages just 1 pod. This being a master probably makes sense in this case. And you'll see this pattern quite frequently, where we have 1 master pod managed by a replication controller just to make it highly available. Okay, so we've got past all of the Kubernetes key concepts. So let's talk about, no we haven't, nearly this one. This slide, finish this one. I've been distracted because I just had my photograph taken. So, Kubernetes load testing service now looks like this. One of my labels is out of sync. It should be animated. So we have a replication controller looking after a master pod. And it cares about 2 labels, role equals master and name equals locust. And we'll look at that shortly. And the other replication controller has been asked to manage 4 of these pods with name equals locust, role equals worker. I haven't shown all of the labels on there. But basically, we have 2 replication controllers. And so now that is our desired state that will be maintained for us by both of those replication controllers. So let's talk about deployment. So to get Kubernetes up and running is fairly straightforward. It's dependent on where you're trying to deploy it and maybe whose workshop you're in. If you go to see a Kelsey Hightower workshop, you'll build it from scratch, and it's fantastic. It's really informative, and it shows you exactly how Kubernetes works. And those videos are online as well. You can look at them, and it's very, very useful. But it's also fairly straightforward to launch Kubernetes, to create a Kubernetes cluster and get it up and running using scripts for various different providers. And really what you have to do is choose your platform, whether it's GCE, AWS, Azure, Rackspace, on-prem, laptop, whatever. And ultimately choose a node OS. Again, your mileage may vary depending on which provider you use. Because GCE, for example, will choose one for you. It's probably customizable, but you've got to be careful. You really want a hardened Docker runtime to be able to run this. And so you choose a node OS, could be Core OS, Atomic, Red Hat, Enterprise Linux. No, Atomic, Red Hat, Enterprise Linux as a Commodore. It shouldn't be there. Debian, CentOS, Ubuntu. And then you're going to run a script, probably kubeup.sh. And you may change some configuration parameters before that. But ultimately, that script will run. It will do various things with scripts. And depending on where you're using it, it could be salt stack. And ultimately, you'll end up with a cluster configured and ready to go. The individual steps are to provision the machines, to boot all of the virtual machines, install and run your kube components, configure your networking. You may have to install Flannel to make this work. All of the IP ranges for pods and all of the services and SDN. Then start all of those ancillary services that make up Kubernetes, the things that Kelsey walks through installing them and getting up and running. And ultimately, you have to continually maintain your cluster, doing upgrades and OS updates and such like. So that's not the easy or the fun part, depending on who you are, because I always find that stuff fun, right? So I like doing it. Although, whenever you hit problems, it was a bit of a nightmare. So this is where something like Google Container Engine or other providers who provide product-ready solutions of Kubernetes really come into play because they take care of all of that for you. Basically, to deploy a container cluster on Google Cloud Platform, just press one button. And we're going to talk about visualizing Kubernetes shortly. We're not going to talk about it. We're going to show it, and this is the way it works. We basically are able to proxy our API. We have to authenticate. Once we've authenticated, we can proxy the API and do everything locally, and that's what we'll be doing today with this demo. Clicker. Where's my clicker? So, how many of you are familiar with Locust load testing tool? Okay, one of you. So now you're all familiar with Locust. And next time I ask, you'll be able to put your hands up. So I did say that in the blurb for the talk, I was going to talk about JMeter and Gatling. So I've been working on JMeter because I like JMeter. I've been using it for a long time. But I did have some issues with demoing it. Not necessarily getting it up and running, but actually showing it in a useful way. So some of you who've used JMeter might understand where I'm coming from there. But it's a little bit more complicated than I would like, and I think it might be hard to demonstrate very well. So I'm going to go a little bit simpler using Locust. And also, Gatling is not really designed for distributed load testing, although probably somebody in the audience would correct me at some point, and they have some way of doing it. This is written in Python, sorry about that, but it's pretty good Python. It's fairly easy to understand and pass, and fairly easy to customize because it is open source, so you can change this thing to do whatever you want to. And it's also very easy to get started with, which is one of the reasons why it's so attractive for a demo. Because the problems you have with demos go up exponentially compared to the complexity of it. That's my rule. So, the deployment steps for Locust. The first thing we have to do is build a Locust image, a Docker image, and push it to a repository. We have the image actually stored in our container repository within Google Cloud Platform. And we're going to pull it down from there rather than from Docker Hub. We've already built it. I'm not going to build it because, again, it's one of those things that if you have a crappy Wi-Fi connection, you have a slow machine, various other things come into play, it could take 5 to 10 minutes to build an image. And I don't want to be standing here waiting it to finish, trying to fill in time, because I'd have to tap dance, and that would be funny. So, none of you are laughing. Laugh at me. Right, so after we push the image to the repository, we need to deploy our worker replication controller. Actually, I've got it in the wrong order. It should be we deploy our master replication controller, because our workers like having a master to talk to. So we deploy the master replication controller, then we deploy the worker replication controller. Then we deploy the service that we saw in the diagram previously, and we create a firewall. And some of those things have already been done for us, like the firewall itself. And in this case, we're going to be deploying it on Google Cloud Platform, on Google Compute Engine, not on Container Engine, because we're using 1.1 of Kubernetes. And Container Engine doesn't currently support 1.1, but it will shortly, I think. Expect shortly. Must be some value of shortly. So we created the firewall. We've got the image available. We really have to create the replication controllers and the service. Also, one thing we talked about earlier about lookups, service discovery and DNS. It's very easy for the workers to discover the master and connect to the master because they can just look it up in DNS. So once we've created the service, we can connect to the service via its DNS name. And the second part of that slide, which I'm going to demonstrate shortly, is there. So here we can see we have locust master and its value, which is locust master. That's an environment variable. And the scripts that we use to start locust, both the master and the worker, can say ---- master host equals $locust master and pull that from the environment. And that's how that works. So that's how we wire things together through environment variables. And so this is where the fun begins. This is Ludovic Champenois. He's still reading my slides. So. He's doing a talk on Friday on App Engine, by the way. It's going to be good. I may join him for that. I'm supposed to be joining him. Right, okay. So the first thing we're going to do is make sure we have... Is that too low for everybody? I'm going to move it down, move it up there. I always have this problem. And wow, it's so quiet. So we run kubectl version. And kubectl is our command line tool for Kubernetes, and it does everything. And yep, so kubectl version, major 1, minor 1 plus. So this is 1.1, which is what we need to do what we're going to do. And the first thing we're going to do is deploy our locust master. And we're going to do this from a configuration file, which I'll show you shortly. And it's located in a directory. And here we have a nifty little visualization that we're going to use to visualize the whole thing. And I'll make this bigger for now. I may have to resize it a little bit. So our visualizer is proxying the API. It's talking to the API locally on my local machine and saying, get me all the pods, get me all the services. At the moment, it's doing it in a tight loop, and it's not very efficient. And it means that I can't drag things around. This is JS Plum, by the way. But it means I can't do useful stuff because it gets refreshed all the time. We're working on that, working on fixing it. So basically, we have a pod, locust master, name locust master, role master, which is the labels, and also we have a replication controller. You can see it's selector at the bottom, which is the labels on the pod, and we can also see number is 1. We want 1 of these pods. It also has a template which you can use to create new pods if anything horrible happens to the one that's running. So, oh no. I'll come back to that in a second. Next thing to do is create the service. So we want a service. And that's the service, up in green. And here again, we can see the selector. It's selecting on the same values as the replication controller. It doesn't have to. It could be completely independent of each other. But in this case, they have the same labels. And you'll also see an IP address, which is an IP address for internal purposes. So we can access this service on 10.0.121.18 from within the cluster. Very, very shortly, and this is happening in the background, Google Computer Engine is setting up a forwarding rule that will expose our port externally. So we'll go back to that in a second. But it takes a few minutes to set up the plumbing. And I've always kind of never really questioned why that is. Why does it take so long? Perhaps I should do. And then we're going to deploy the worker controller. Okay. And now it's going to reconfigure itself a little bit. I've not got this. Let's just look at the workers for now. So the worker here has, so the worker's only got one pod as well currently. We're going to scale that shortly. But it has a selector in the replication controller, and it also has one pod. So we have two pods, this one here and this one here, and we have one service and two replication controllers. And I'll make that fit. All right, okay. So the next thing to do is go back to our IP address for our service, which has now appeared. We'll open that in a new tab. And we can go to Locust. And we have one slave ready. This is Locust. This is its user interface. It's very basic, but it does the job. So we have one slave ready, and that's our worker. We'll scale that later and see that change. So what we can do, we have a very simple application running on App Engine. It has two endpoints. One is /metrics, and the other one is /login. And basically, we're kind of emulating a very, very simple IoT setup where metrics are being pumped out by devices, maybe sensor devices somewhere, hitting the metrics endpoint constantly. Every now and again, they had to re-authenticate and revalidate, and they'll hit the login. And that should happen fairly straightforwardly. So we're going to say we want to emulate 100. And the reason I've gone for low values is because I want to show scaling happen without having to get too much in the visualization. If we had 100 pods running, it'd be very, very hard to visualize. So we could do this at scale, much larger scale than if we wanted to. But for now, we're going to keep it low. So start swarming, and after a few seconds, it will start hitting the endpoints. As you can see, it doesn't do a huge amount. Those response times are very, very low, and we don't get any failures. I've not seen many failures, except when I was pumping away on the wrong endpoint, which is the one that came with the original demo, and I was hitting it around 2,000 QPS. I think I must have got banned from hitting that application. So here we see everything that's happening, and that's good. We have distributed, yes, we only have one worker currently, and that's doing all of the work. So we want to be able to scale that. And so what we're going to do here is go back to our slides and see if I'm jumping ahead of myself. So the scaling example, and I'm not going to do this bit specifically, I'm just going to walk through the slides, because I want to actually jump to auto-scaling and show that instead. So here's a scaling example. We have one pod. Replication controller, name equals locust. In this case, it's locust-worker, and role equals worker, one pod. And so we have our pod. And you can see we have one slave. And then we change that to 2, tell the replication controller to change it to 2, and it will tell the API to create another pod for us. Now we have 2 pods and 2 slaves. So lastly, we go up to 4. And again, that's reflected in the user interface where we have 4. And this is from a test I did earlier when I was just going to do scaling, manual scaling, before I decided to get all fancy and do automatic scaling. So that's how we scale. And let's talk about scheduling and how this works and how we can prioritize things on Kubernetes and get the best results and the best utilization out of the resources that we have available to us. Because we have lots and lots of machines, but we don't want them to be sitting around idle. We only want to invest in machines that we can use. If we had to invest in maybe a headroom of 50%, that would be huge for us. That would be massive. It would cost us a fortune. And even at smaller scales, 10, 100 machines, that's still significant. So you want to be able to maximize the utilization of all of your resources, your compute resources, your CPU and your memory. And so for this, we use something internally called resource-based scheduling and other things as well. But also Kubernetes uses resource-based scheduling as well. And that's fairly new and fairly nascent. It's coming along quite quickly, and it's going to get really interesting very soon. So basically, resource-based scheduling will provide quality of service for scheduled pods, or allow us to provide quality of service. Quality of service meaning guaranteed amounts of CPU and memory that they can have. Because we want some things to run at a higher priority than others, we may actually say, I don't care so much about this pod. I don't care if you run it, just run it when you can. And if this is a dynamic cluster where we have pods being scheduled and unscheduled quite dynamically throughout the day, then that's quite likely that we have some smaller, lower priority pods that will be kicked off the machine and pushed back into pending while other things use the resources, and then schedule back on again when those resources become available again. And so we have the ability to specify for each container CPU and memory requirements. And also we can specify a request. This is how much CPU and memory we think we're going to need. And also a limit. This is the maximum we're going to allow this pod. So we're kind of making a guess, maybe, hopefully, an informed guess. And we'll talk about that in another talk one day, how we actually get all of these numbers. We're going to say this is what we think it's going to use in terms of CPU and memory. And this is the limit that it ever can have. It can never go above this. Okay? And what's going to happen in future releases, we'll have three classes of quality of service. One is going to be best effort. And in that case, we're going to say request equals 0. I'm not requesting any resources for this. So just run it when you can. So this is best effort, effectively. This will only run when there are resources available, not being contended by anybody else. So these will run eventually, but only when something else comes off of the cluster. The next one is burstable, where we have a request and we have the limit. And the request basically says, this is what I expected to use, but it is allowed to use up to here. And it can peak if it needs to. That's what we call burstable. So that would be the second tier of a second class of QoS. The last one is guaranteed. Now, this is the highest priority jobs where we say the request equals the limit. What we're requesting is the maximum you should allow it. But at the same time, it's not just the maximum. It's saying we want you to give all that resource up to the limit straight away. So this is likely where you should stop. But we want this thing to run and be guaranteed to run. And so this is the next highest, well, the highest quality of service. And pods that are running at guaranteed should never be preempted. Again, until we get some more finer granularity around priorities, maybe that's not the case. But they may be contended with other things that also have guaranteed. But ultimately, this kind of best effort scheduling improved our utilization by about 20%. So now we can actually say, best effort, we don't care when it's run, or burstable, we can have this if it needs it, but if it's not available, we can't have it. These things are really high priority, we want them running all of the time. Okay? So that's how we get our efficiency, some of the ways. And in terms of declaring this, we do this within a configuration file. I'll show you the configuration file shortly. I have to open up the... let me do it now, actually. So these are the configuration files. This is the Locust master controller. Some of the things on the slides there. I'm not going to go into too much detail on these. This is the worker. It's just a YAML file. We don't expect you to write YAML. Ultimately, you'll have other systems, maybe CI systems that create this configuration for you dynamically and push it out straight to Kubernetes. Or maybe you'll even have a PaaS that abstracts all of this stuff away, something like OpenShift or maybe a Google App Engine in the future. And it'll abstract all of this detail away. But for now, you create configuration files. And also, the service as well has something interesting that I wanted to show you, which is type equals load balancer. Where is it? Yeah. So down here, so having this line, type equals load balancer in my service configuration file means I want you to create, if possible, if the infrastructure supports it, an external load balance endpoint. Okay? So that's what the configuration files look like. So here we have the worker controller, and we specify a request of 300 memory, 300 milli CPUs, and a limit of 300 megabytes and 300 milli CPUs for the limit as well. So this is a guaranteed one. We want this one to be guaranteed to run. So also let's revisit cluster nodes before we get to auto-scaling, which is the most important part of the talk, right? So cluster nodes we visited, we looked at these already. How do we find the nodes we want to run this stuff on? This is extremely important, and we're going to dive into this in the demo. We need to ask questions when we get a request to schedule a pod. What resources does it need? So how much memory and how much CPU is it requesting, or what is its limits? Does it need a specific disk? In which case, we need to either mount that disk or schedule it on a machine that has that disk already mounted. What node can it run on? Does it require a specific node by name? And again, this is very snowflakey. This is not the best situation. It means you know there's something about this machine that's special, and you want to run your pods on it, or some pods on it. And it could be that this is the only machine that has 32 gigabytes of RAM, and you have a pod that needs 28 gigabytes of RAM to run, so you can only run it on that node. You could do this through labels, though, as well. And also, what nodes can it run on labels? Does it need SSD disk? Does it need GPU or some other special characteristic of that node? So that's the first thing the scheduler does. It tries to work out what nodes can possibly run this pod. And then we're going to rank those nodes individually to find out which one we should ultimately schedule it on. And we had different policies, many different policies, and they may have changed in 1.1 slightly. When I first wrote this slide, the default was to balance CPU and memory out. So we tried to make sure the CPU and memory were the same. So rather than consuming all the memory and running out of memory, we would try to make sure they were balanced. But we can also prefer the node that will have the most free resources left after the pod has been deployed. Or we can prefer nodes with a specified label. Or we can also try to make it such that we minimize the number of pods that are running on an individual node for each service. So we have a service that has 10 pods, we have 10 nodes. We won't run all 10 of them on one node, making it extremely dangerous if that node goes away. So there are different policies we have, and you can even write your own policies for this. It's called a mission control. So let's explore CPU and memory load balancing, or balancing. Machines, in my opinion, have shapes, both virtual and bare metal. And workloads have shapes too, which is interesting. So in a container cluster, effectively, these virtual machines, which will eventually go away, I'm looking forward to the day when the virtual machine goes away. At the moment, it's just really effectively a resource boundary. It has a certain amount of CPU, it has a certain amount of memory. You can't really run anything bigger on it than that memory or that CPU. Although we can overcommit quite dramatically if need be. We won't talk about that today. But generally, the machine has really just become a resource boundary. And so these are typical machine shapes where we have 4 cores, 8 gigs of RAM, 8 gigs, 2 cores, 8 gigs, 1 core. The workload shapes are a little more arbitrary, 1 gigabyte, 1 core, 3.5 gigabytes, 1 core. But they have shapes, and ultimately we can play Tetris with them. And Kelsey Hightower's done this already. It's like, he did it on the same day I did it as well, at Container Camp. So playing computer Tetris is like this, and it's just crappy animations, I'm afraid. I should build a game to make it work. But basically, we have a job, 2.5 gigabytes, 1 core. And now what we see with that job is we have the CPU is fully utilized, but we have 5.5 gigabytes of RAM that's inaccessible. We can't use that. And so basically we've stranded that resource. That 5.5 gigs of RAM is completely inaccessible to us. And that's a problem. What we could do is we could take a different machine, and we have a scheduler that's sensible about this. It can say, I'm going to schedule it on this machine, which has 2 cores and 8 gigs of RAM. And so now we see we have resources, both CPU and memory available, and we can therefore run a different job on it. So now we have all of our CPU fully utilized, and most of our memory fully utilized, and that's efficient bin packing. And that's one of the principles we use internally at Google. So efficient scheduling is ultimately the key to container management. So let's talk about autoscaling and how this works. So we'll start off, we'll go back to this shortly, but let's show this in real time. The first thing I need to do is create a configuration for my autoscaler. And I go back to Atom, I can find my YAML file here. And this is still in beta, so this may change at some point, but we can specify the minimum number of replicas, the maximum number of replicas, and also a target CPU percentage. Now this is taken across all of the containers in the pod, and then averaged out across all of the pods. Okay, and so we effectively take the utilization that we want, the amount we've used, and then divide them together and get out a number, which ultimately will give us the number of replicas that we should have. And so it does this calculation dynamically every 30 seconds or so. And let's deploy that so we have one actually deployed. So we're going to deploy this. This is an object, by the way. It has a kind, which means it's an API object that we can deploy. And so we're going to do okay, so now we have HPA, as we call it. So fortunately, they've shortened it, so it's easier to say, or easier to write. We can get to HPA, which is, oh, that's interesting, 170% utilization already. Okay, that's kind of worrying. This is why you should never do demos of autoscaling. I did one at Google I/O last year, and it was really dangerous, but something interesting may happen now, and we should probably go and see that. But we can actually watch that as well. So we can actually wait for changes using the API. We're constantly polling the API to see what's happening. Well, we're actually getting a stream of data back and listening for that. But let's do one other thing first. Let's look at our individual nodes. And we have 2 nodes in this cluster. No, we don't. We have 3 nodes. Oh, no. I forgot to rescale my cluster. Oh, well, never mind. OK, so we can actually look at each one of those. And this will give us a summary of the pods that are running on that node, and also what the available CPU and requests are for us that we can actually use and get access to. So we have a bunch of pods running on this. We've already scaled our nodes already, our pods already, our worker pods. We also have a bunch of system pods as well. So there's many pods that have already been scheduled. Things like FluentD, the DNS service, all of these things are scheduled as pods as well within Kubernetes. And so we could do this for each of the pods, but let's go back and revisit our viz and see what's happened. Okay, so now we have 4 workers. So it's automatically scaled already. So it saw that there was 170% CPU utilization, which I got to admit has taken me completely by surprise because we're only running 100 users and it shouldn't have done that. But these things are always strange and esoteric. So let's go back to our Locust interface. And again, this can be a little bit quirky as well. We can see it says 4. It's picked up the change that we now auto-scale to 4 pods and workers. So I'm now going to bump this up to, I'm going to bump it up to 500 and see what happens. And again, this may break horribly because I've never, with this particular configuration of memory, I've never gone up to 500 users. So we'll do that now. And we'll go back to the slides and we'll leave that to cook for a little while. We may kind of just break this down here. And just press send from the slides here. No, we'll do it properly. So basically, this is our maybe potentially our original configuration where we have a replication controller that has 2 pods to maintain. And the 2 pods are there, they have the labels which the replication controller is selecting on. Then we have this thing called Heapster that uses an internal service called CAdvisor that is able to monitor the running containers within the pods and get statistics from them. And in this case, at some point, Heapster says, it's got 40% CPU and 70% CPU. Averaged across them, that's over 50%, which is our scaling target. So now what we want to do is be able to scale that. So we changed on the replication controller, number of pods to 4. That was done by our calculation, and ultimately, the replication controller will now create the other pods, and now we've auto-scaled. That's exactly how it works. That process is continuously ongoing from the scaler. Go back to our, hey, where's my, right, it's over here, right? It hasn't scaled again yet. Maybe bump it up even higher. And we can go back to our HPA and watch it. So it's potentially at 41%. But again, we're not seeing everything that's happening. I'd like to be able to do this calculation live in real time. But at the moment, I can't be sure that it's 41%. But we're still ramping up at the moment. So let's go back to the slides. So also, the auto-scaling was introduced in 1.1 as a beta feature. So that's available today if you build your own Kubernetes. Not available from every provider, but it will be fairly soon. And also, with Google Compute Engine and also Google Container Engine, you can also scale automatically your nodes, the number of nodes that you have. And this is done through Compute Engine managed instance groups. I'm not going to demo it, because it's going to be hard to actually overload my system. But at some point, if we scaled that up more and more, we'd have so many pods we could no longer schedule them, because they're asking for specific resources. And so we wouldn't be able to schedule every one of them, and some of them would sit in pending. At that point, we could scale out our cluster. We could do it manually by going into the cluster and resizing it, or we could ultimately hook up the autoscaler, which is already available in Google Compute Engine, and also scale it dynamically. And for that, we have this metric called kube target node utilization, which is a custom metric delivered through our cloud monitoring service. And ultimately, that would scale all of the nodes for us. And the final thing was to go back to see where we are. So now we see we have lots of pods, but we don't have them all scheduled. The yellow ones are ones that are unable to be scheduled currently. They are impending. So they're waiting for resources to be made available to actually be able to schedule them. And what we could do here is go into our cluster. This is Compute Engine. This is the Google Developers Console, the new beta version of it. And we can select Compute Engine, which we've already done. Select instance groups. These things run in a thing called an instance group. Currently, we have 3 instances in that group. And what I'm going to do is edit it and bump it up to 5 and see if we can get them all scheduled. That will take a little bit of time, and we'll go back to the viz to see what's going on with it. We have quite a few pods running now, more than I expected. It tends to slow down the user interface as well. So, okay, that's good. Last slides. So, Kubernetes. The status currently is that it's in 1.1, and that's since this week. It was announced at KubeCon in San Francisco this week. Google Container Engine, which is effectively hosted Kubernetes. We don't have high availability with Kubernetes currently, but by looking after your master for you, taking it out of your hands and taking it out of your control, we can effectively make sure it's always up and running. So we take the master, we push it to one side, you no longer have any visibility on it, and we make sure it's continuously working. Container Engine went GA in August 2015, but there's plenty of other options for running Kubernetes. In terms of platform as a service offerings, Red Hat, OpenShift, Deis, Stratos, Chorus, Tectonic, Mirantis Murano, Red Hat Atomic, Mesos, and Mesosphere. They also have it as well. So check out Kubernetes. Container Engine, again, we've already talked about this, manages Kubernetes uptime. And the resources for this session, which you'll get the slides for, which you can just follow, we have a solution that's based on this talk. Well, my talk's based on the solution, actually. And also we have a GitHub repository with everything in it, everything you need. And we go back to our check to see if our nodes are up and running. They are up and running, but they won't be all ready yet. So we'll start scheduling some of those pods soon. All right, anyway, so we'll wait for that to happen while we're asking questions. And I'll just go back to the last slide, which is this one. And yeah, Kubernetes is open source. Everybody's contributing to Kubernetes. It's really, really got a big buzz to it going. Kubernetes.io is the documentation and everything you need to know about Kubernetes. It can be found there. Go to github.com/Kubernetes. I'm going to change this now because it is available from that path, but it's also available from this path as well. GitHub.com/Kubernetes. On Slack, we have a Slack channel, #Kubernetes users, and on Twitter, @Kubernetes.io. And that's the talk. And I'll take questions now if you have any. Where are the microphones? Do you have microphones? Okay, so any questions? I can't see anybody. No? No questions? Wow, okay. You're hard to please. All right, no questions? Is there a process for doing questions? No? Okay, all right, thank you. Thank you for taking your time. Thanks.